Okay, so this is the last of our lessons for this topic of integration. This is lesson 30, Fundamental Theorem of Calculus, part 2. So in the last lesson, we talked about what happens if you've got the derivative of area function like this one, f of t dt. And what we discovered was pretty much just equal to f of x. Of course, if the x was a bit more of a complicated term, we had to use the chain rule and we had to multiply by the derivative of the upper limit. But essentially, that's what we've learnt. So the rate of change of the area function is equal to the height of the graph at x. So today we're going to look at something a little bit different but also very similar. So for this warm-up activity, below is a distance time graph. So we've got the time measured on the horizontal axis and distance measured on the vertical axis. And this is just a straight line. So if we wanted to work out the speed, speed is equal to distance over time. And so essentially, it's the gradient of this distance time graph. So we can pick any points. We can say, well, we've got a speed of, say, 80 there. And initially, we have a speed of 55. So we can say 80 minus 55 over 1 hour. And we end up getting a speed of 25 kilometers per hour. And for this particular graph, the speed is constant. It's always 25 kilometers per hour. So now what we want to do is plot the speed versus time on the axis below. So we've got time on the horizontal axis, and we know it's constantly 25 kilometers an hour, so 25 is right there. So if we plot in this line here, it's just going to be a straight line like that. And using the graph, is it possible to calculate the distance travelled from t equals 1 to t equals 3? So from our speed graph, if we want to get to distance, we need to possibly look at the area trapped underneath it. So let's try that. Let's try from t equals 1 to t equals 3 and calculate the area of that section there. So check out this integral. So it's the integral from 1 to 3 of our speed graph. So we know it's 25 kilometers an hour, and we know there's 2 hours, right? So it's going to be 25 times 2, which is 50 kilometers. And so let's have a look up here. So from time equals 1 hour to time equals 3 hours, have we travelled 50 kilometers? Let's have a look. So we're going from 80 to 130. Last time I checked, that was definitely 50 kilometers. So from the distance time graph above, where can we find the answer to question 3? The distance travelled between t equals 1 and t equals 3. Well, the distance travelled is the difference in the y values, isn't it? The difference in the distance values. So that was f of 3, which was 130 kilometers, minus f of 1, which was 80 kilometers, and we end up with both having 50 kilometers. Okay, so what can we conclude? Well, the area under the curve of a derivative function, like our speed graph, another example would be velocity, is equal to the difference in y values in the original function. So another way we can think about it is if we write this as a general rule. Here we've got the definite integral of a derivative function, and when we anti-differentiate it, it's the difference of the y values of the original function. And that kind of makes sense as well, because when you anti-differentiate f dash of x, you get f of f of x, and if you treat this as a definite integral, we just plug them in. So it should make sense intuitively that when you take the integral of a derivative, you end up with the original function, the difference in the original function values. So here we go, we've got a couple of examples here where we anti-differentiate first. So we get x to the 4 over 4. And then we're subbing our upper and lower values. Of course, we don't need the plus c because it's a definite integral. So putting 3 in, so it's 3 to the 4 over 4 minus 2 to the 4 over 4. 3 to the power 4 is 81. And 2 to the power 4 is 16. And 18 minus 16 is 65 over 4. So that's the first one. This next one, same idea, anti-differentiate first and substitute in the upper and lower limits. So sine of theta turns into, if you remember our order, we've got sine, cos, negative sine, negative cos when we're differentiating. So when we're anti-differentiating, we go in the reverse order. So the antiderivative of sine is actually going to be negative cos. So we've got negative cos of theta between pi on 2 and negative pi on 2. We sub in those values. We end up getting negative cos of pi on 2 minus negative cos of negative pi on 2. Cos of pi on 2 is 0, and negative cos of negative pi on 2 is also 0. So all up, that one is 0. And then here we can use some properties of definite integrals to calculate this part. So if we've got the initial, integral, we'll notice that the limits are a little bit backwards, back to front, like the bigger value is at the bottom and the negative one's at the top. So what we'll end up having to do is having to flip it. And when we flip it, that's going to equal the definite integral from negative 2 to 1 of f of x dx plus the definite integral from 1 to 3 of f of x dx. So notice our original starting point is negative 2. There's our original starting point, negative 2. And then we're finishing at 3. And then we're finishing at 3. So we're just using 1 as a intermediate part, I guess, of this particular question. So this first definite integral is equal to 2. So if we substitute in 2 into that part, and for this definite integral, the definite integral is equal to negative 6, so we substitute negative 6 in there. So our total integral from negative 2 to 3 is going to equal 2 plus negative 6, which is equal to negative 4. But what we actually want, we want the definite integral from 3 to negative 2 of f of x dx. So that's going to equal the negative of what we've just worked out. So the negative of negative 4 is positive 4. So that's that one. Okay, for these exercises, again, I'll put all the solutions to these questions on OneNote. I really want you to have a go at 1C. This one's a good one because there's quite a lot of steps you need to do to simplify if you're trying to do it by hand. So try and do these questions without a calculator. And the other ones I want you to do is E and G. Again, check OneNote for the solutions. I've got all the steps, particularly for part C. That took a little bit of time to get that one. And then for these ones, try and use the properties of integrals to work out how to simplify these, just like the last example we've done. So 2 and 3 is properties of integrals. And here we've got reverse chain rule. questions, so 5 and 6. And for questions 7 and 8, I will go through these ones now because these ones are a little different to what we've done in the course so far. And this requires, I guess, a little bit of extra understanding as well. So, and maybe transformations of functions. So I've developed a formula, a rule that can simplify these questions and make them a bit easier to calculate. So we'll test it out for question 7, and then you can see if you can do it for question 8. And I've got the instructions on the solutions on OneNote. So here's my formula. If you've got a question where you've got some kind of a definite integral from a to b, and something's going on inside the brackets to this function. So we've got 3x, so we're going to call it kx dx. If you wanted to simplify it, in other words, if you want to transform this back to the original function, you have to think of these type of questions as reverse transformations. So in other words, to transform something that goes from f of 3x back to f of x, what we need to do is divide the integral out the front by k, and then we need to multiply the upper and lower limits also by k. So a times k and b times k, and then we'll end up getting our original f of x function. So this rule is very useful in trying to calculate these type of questions, because what we're going to do is apply it for question 7. So in this one, k is equal to 3. K is the number in front of the x in there. So what we're going to do is we're going to say, okay, if k is equal to 3, we're going to go 1 over k, 1 over 3. The upper and lower limits, we're going to multiply by k. So we get a times 3. So in this instance, it's 0 times 3 is going to equal 0. So 0 times 3 is 0. And then if we go 3 times 3, so 3, oops again, 3 times 3, so 0 times 3 on the bottom and 3 times 3 on the top. So that's what we're changing the limits. And then we can transform our function, go back to what we had originally, so f of x dx. So now we've got 1/3, and now we've got the definite integral from 0 to 9 of f of x dx. And we get told that the definite integral of 0 to 9 of our function is equal to 5. So with all these type of questions, they give you enough clues to be able to then substitute it into it, and we know that the answer is going to equal 1/3 times 5. So that's 5 over 3. So the definite integral from 0 to 3 of f of 3x is going to equal 5/3 of what the integral is from 0 to 9 of the function. Okay, might as well help you with 8 as well. We ready? If you want to pause 8 and give that a try for yourself, essentially what we need to do is use k equals 3 again, but then we're going to have to transform and do an extra I guess transformation to get rid of the +1 to get the original function. So if k equals 3, we'll do it again. So 1 over 3 at the front, so 1 over k. We change the upper and lower limits. So the first one we go 0 times 3, and the top one is 1 this time. So 1 times 3. But instead of it being f of x now, it's going to be f of x plus 1. We've got rid of the 3 at the front of the x, but we haven't got rid of the 1 yet. So if we do that, we end up getting 1/3 the definite integral from 0 to 3 of f of x plus 1 dx. Now, if we wanted to transform, if you ever want to go from f of x plus 1 to f of x, you got to think of this as reverse transformations. So when we're doing reverse transformations, normally we think of going from f of x to f of x plus 1. And so when that happens, we go 1 unit to the left. But this time, because we're going the opposite way, we're transforming it to the original function, we actually have to think about moving 1 unit to the right. And that means the x values add 1 to them. So the upper and lower limits of the x values, these ones here, this 3 and this 0, we have to add 1 to them. So 1/3, 0 plus 1 is 1, and 3 plus 1 is 4, and then that will get rid of that f of x plus 1 transformation to get us to f of x. And now that's convenient because in the question they say the definite integral from 1 to 4 is equal to 5. So we can replace all of this bit in here with 5. So 1/3 times 5 is equal to 5 over 3 again. So both answers are 5 over 3, which is a bit of a bit lucky, but that's just the way it is. So in terms of practice for the test, there's heaps of practice in the Chapter 6 review of the textbook. A whole bunch of short answer questions and a whole bunch of extended response questions. You've got math space that you can work on as well, where you can just choose any particular topic in integration, any chapters in the integration chapter. And then we've also got 3 times practice tests on sector under assessments. So the test is still next Tuesday of week 10. And it's all on anti-differentiation, integration stuff. So yeah, plenty of practice for you to work on, but now it's up to you to get some work done, work through the practice tests, get some math space done, and then see how much you can get done before next Tuesday. All right, thanks everybody. All the very best. Bye.